All right, welcome back everyone to our Calculus 3 class notes and Chapter 14 on partial derivatives. And we're entering the last section that we're going to cover in Chapter 14. And this section is about Taylor's formula. Section 14.9 is Taylor's formula for two variables. Okay, so we all learned Taylor's formula back in Calc 2 for a single variable. So now we want to talk about Taylor's formula for a function of two variables. So for a function f of xy at the point AB. So suppose f of xy and its partial derivatives through order n plus 1. So all the partial derivatives, all the mixed partial derivatives, etc. through order the n plus first derivatives are continuous throughout an open rectangular region R centered at the point AB. Then throughout R we have the following. So f of a plus h, think of h and k as just a little bit, right? Because we always want to approximate the function using Taylor's formula near where we've constructed the formula. So h and k are just a little bit. Some books will write it as a plus delta x, b plus delta y. We're just calling them h and k. It's not that important right now, so don't worry too much about it. But f of a plus h, b plus k is going to be equal to, well, whatever f is at ab. And then we take the first partials, f sub x and f sub y, evaluate them at AB, and you multiply the partial of f with respect to x times h. So h goes with the x component, and the partial of f with respect to y times k. Okay, and then rather than reading this whole formula to you, you can see the pattern as you go through. So pattern for the second derivatives is 1, 2, 1. You multiply the full partial derivative with respect to x, second partial with respect to x times h squared, the h piece. The mixed partial hy is multiplied times hk twice, and that's because f sub yx and f sub xy are the same, so we don't have to do both. As long as the partials are continuous, then these derivatives are the same. And then you multiply the full second partial with respect to y times k squared. Again, evaluating it all at AB. And then the coefficients here, actually, this one's 1, 2, 1. The next one is 1, 3, 3, 1. Right, so I don't know if you've ever heard of Pascal's triangle that would keep track of these as you went, but essentially it's applying the binomial theorem, which you may or may not have spent some time on in Calc 2. But don't worry too much about that. It's just that you would take this operator here on f to the nth power, which means, you know, whenever time you can take it to the nth power, that would be the nth derivative here, right? Nth derivative here. Okay, so you just have to understand how this operator works. The binomial theorem will give these, but Pascal's triangle also is a quick way to remember these. We're not going to do anything beyond the second or third order approximation, so you don't need to worry much about that, okay? Just want you to understand what the whole formula is and how far out it could be carried. So that gives an approximation for f of xy near the point AB. The last term, this term, is actually the error term and is evaluated at some other point, a plus ch and b plus ck. So that's on the line segment that joins AB and A plus H, B plus K. So remember, this is just a short line segment because we're not going far away from AB. And then even shorter, go somewhere in before you get there. That will be the error term. And so then really you just try to find where's the point on here that maximizes this error term. Okay, now if AB equals 0, 0, this is what we're going to really focus more on. This is much easier to understand. It's kind of equivalent to Maclaurin's polynomial, Maclaurin's theorem back in Calc 2, because that's doing a Taylor polynomial approximated near 0, 0, and that's still near the origin. So we are also still doing near the origin. Okay. Now what you do is you look back up here and you treat h and k as the independent variables. Okay, and I'm just going to call them x and y, just understanding. So this h and k, I'm calling the independent variables. A and B are 0 and 0. And I'm just going to call them x and y, just remembering that x and y are really close to 0, 0. This approximation is best the closer we are to 0, 0, of course. So that leads to this formula. And then everything here is evaluated at 0, 0. I just didn't write that at this point. But the formula is the same. Okay? So notes here are that the first n derivatives are evaluated at 0, 0. The last term is the error term, is evaluated at a point on the line segment joining the origin in xy, just like the error term when we had it at AB. Taylor's formula provides polynomial approximations of two variable functions. The first n derivative terms give the polynomial of degree n. And you have to remember, like something like x times y, both of those are to the first power, but together that's a second degree polynomial in terms of x and y as being the independent variables. The first three terms, f of 0, 0 plus x f of x plus y f of y, give the function's linearization. And to improve on the linearization, so that would be a linear approximation. To improve on that linearization, we add higher power terms. And again, the last term gives the approximation error. Okay, I'll come back and I'll go through these examples one by one.